Welcome to The Debate. I am your host, and today I'm arguing for the position that humanity has sort of outgrown the passive acceptance of, natural limitations. If we want to survive the next century, we have to take the wheel, actively intervene, engineer, and really upgrade our environment through high technology.
And I am here to argue the counterpoint. I think that true scientific advancement isn't about overpowering nature with, brute force. It's about understanding the elegance of the systems already in place. My stance is that the most sophisticated solutions are the ones that stop fighting physics and biology and instead learn to harness the systems that have been running this planet for billions of years.
And that really is the fundamental friction of our time, isn't it? We are staring down the barrel of a convergence of crises. We have a global population rocketing toward 10 billion people. We've got a climate that's becoming more and more volatile. And we have these critical shortages looming in food, fresh water, energy. So the question we're debating today isn't if we need to act, it's how. Do we rely on our ability to manipulate matter, to rewrite genetic code, split the atom, build autonomous robots to do our bidding?
Or do we realize that our attempts to rewrite nature are exactly what got us into this mess in the first place? My argument is that true advancement isn't about building a bigger machine. It's about adaptation. It's recognizing that a simple mesh net catching fog or a microbe fermenting grain is often more efficient, more resilient, and far more sustainable than some billion-dollar desalination plant that needs its own power grid just to turn on.
I think we need to be very careful with that word efficient today. My starting premise is pretty simple. Nature, when it's left to its own devices, is actually incredibly inefficient, at least for the specific goal of keeping billions of humans alive and, comfortable. Nature's chaotic. It doesn't care if it rains in the wrong month or if the soil is nutrient poor. We can't rely on the serendipity of rain or the lottery of geography. We have to engineer certainty.
Certainty is a dangerous illusion when you're dealing with a complex, chaotic system like a planet. But, go on, lay out your case for this high-tech override.
Okay, so let's look at the absolute baseline of survival. Food production. Traditional agriculture, the way we've done it for 10,000 years, is a resource hog. It requires massive amounts of land, it destroys biodiversity, and it just drinks fresh water like there's no tomorrow. But if we look at the science of hydroponics and aquaponics, we see a huge paradigm shift. We're taking the plant out of the biological lottery. We place the roots directly into a nutrient-rich, oxygenated water solution. We aren't just, growing plants and hoping for the best. We're executing a precise chemical equation.
You're treating a living thing like a piece of software to be optimized.
Because it works. In a modern hydroponic system, we control the light spectrum to the nanometer. We control the pH balance. We control the humidity. And the result? We can grow crops using up to, 90% less water than traditional soil farming. That isn't a marginal gain. That is a civilizational shift. We are uncoupling food production from the tyranny of local weather. We can grow lettuce in the Sahara or in the basement of a skyscraper in Manhattan.
I will concede the water efficiency numbers for hydroponics are impressive, on paper. But you're trading water for energy. You have to constantly pump that water. You have to power all those LEDs to mimic the sun. My argument is you're replacing a free system, sunlight and soil, with a billable one that requires this massive industrial footprint just to maintain.
We're trading a scarce resource, water, for a solvable one, which is energy. And we're improving the biological hardware itself. We are now in the mature era of GM foods, genetically modified organisms. This is where we rewrite the code of life to solve problems nature just fails to address. Take the papaya ring spot virus in Hawaii back in the 90s. It was wiping out the entire industry. Nature's answer was basically extinction. Science's answer was the rainbow papaya, a genetically modified variety resistant to the virus. We literally saved an entire economy by editing the code.
As a very specific intervention for a specific virus, though.
It's a proof of concept. Look at the work done at the John Innes Center in the UK. They took genes from a snapdragon flower and spliced them into a tomato to create a purple tomato. And this wasn't just for looks. That genetic insertion massively increased the anthocyanins, antioxidants that can help fight cancer and inflammation. Nature didn't put them there in those amounts. We did. And then when you combine that with autonomous robotics, machines like Flippy, the burger bot, or AI-driven strawberry pickers, you get a system of pure efficiency.
Pure efficiency usually lacks resilience, though.
These robots use spectral analysis to see a ripe strawberry and pick it without bruising it. Working 24 hours a day, processing data in real time, a single robot can pick, I think it's nearly 800 pounds of berries in one day. That is the future I'm advocating for. GM crops grown in hydroponic towers, harvested by AI. It's high-tech, high-yield, and it's entirely controlled.
It sounds impressive, like a well-oiled machine, but machines break. My perspective is that you're focused entirely on throughput. How fast can we make the berry? I'm looking at thermodynamics. How much energy does it cost to exist? True elegance in science is using the natural states of matter, solid, liquid, gas, to do the heavy lifting for you instead of building a robot to do it.
Okay, so can you give me a concrete example where states of matter can outproduce a robot?
Let's stick with water since you brought it up. You want to pump nutrients and run desalination plants. I want to talk about fog catchers. In regions like the Anti-Atlas Mountains of Morocco, specifically Mount Boutmezguider, they are not building pumping stations. They are installing things called cloud fishers. These are just massive 3D mesh nets. They sit there, they do nothing.
So it's passive collection?
Exactly. It's totally passive. They rely entirely on the dew point and wind. As wind pushes fog through the mesh, droplets get trapped, they coalesce into larger drops, and gravity, our free, eternal energy source, pulls them down into a trough. On a foggy day, these passive nets can harvest over 130 gallons of drinkable water per unit. That is pure, drinkable water pulled from thin air with zero electricity, no moving parts. It supplies 1,600 people in that region. That is engineering with the environment.
It is an elegant solution, I'll give you that. But it relies on fog. What happens when the weather changes? You're right back at the mercy of the climate.
And what happens when your hydroponic pump loses power? But look, let's take another example of physics-based engineering, the ice stupa. In the Himalayas, climate change is shrinking the glaciers. So farmers face this critical gap. They need water in the summer for their crops, but the meltwater comes too early in the spring and just flows away.
So they build dams?
No, dams are brute force. They use geometry. Engineers pipe stream water downhill, again, just using gravity, no pumps, and they spray it into the freezing winter air through a vertical pipe. The water freezes as it falls, creating this giant cone of ice.
And why a cone specifically?
It's all about the surface area to volume ratio. A cone has very little surface area exposed to the sun relative to the huge volume of ice inside. This means it melts incredibly slowly. A single 70-foot-tall ice stupa can store 500,000 gallons of water preserved as ice until the summer sun finally melts it, right when the farmers need it for irrigation. They're hacking the melting point of water using just simple geometry.
I have to admit, the geometry aspect is clever.
It's more than clever, it's sustainable. And finally, on your food point, you talk about splicing genes from snapdragons. I point to fermentation. We have been biohacking for, 7,500 years using microbes. When we make cheese or bread, wine, kimchi, we aren't rewriting DNA. We're just creating an environment for lactobacillus or yeast to thrive. They eat the sugars and produce lactic acid or alcohol. This preserves the food and actually creates new vitamins. We're outsourcing the work to the biological network that already exists.
But that outsourcing is slow. And that brings me to the core friction here, which is time and scale. You love the passive approach, and I agree, it has a certain romance to it. But look what happens when a crisis hits a massive population. Look at water management on an industrial scale. In California, during those huge droughts, they couldn't wait for fog. They needed to stop evaporation in massive reservoirs, so they deployed shade balls.
Ah, yes, the black plastic spheres. This is exactly the kind of brute force engineering I worry about.
It is genius in its simplicity, though. They dumped millions of black, hermetically sealed polyethylene balls onto the water. They cover the surface. They act as a physical lid, a sunscreen for the water. They reduced evaporation by 85 to 90%. But more importantly, they solved a chemical problem. The water had bromide, a natural salt. When sunlight hits bromide in the presence of chlorine, it turns into bromate, which is a carcinogen.
So the plastic blocks the UV rays and stops the reaction.
Precisely. It's a physical barrier that stops a chemical reaction. It saved billions of gallons of water and prevented a cancer risk for millions of people. It is a scalable industrial solution using basic materials.
But at what cost? That's the question you always have to ask. You're introducing millions of plastic polymers into the drinking supply. We know polyethylene degrades over time. It sheds microplastics. And the heat absorption from those black balls can alter the water temperature, maybe promoting bacterial growth. It's a solution that solves one problem but creates 3 new ones down the line. It's treating the symptom, not the system.
But if you don't use the balls, the water either evaporates or it becomes toxic. What is the passive alternative for a billion-gallon reservoir?
Well, you look at desalinization or natural separation. Look at the Salar de Uyuni in Bolivia, the world's largest salt flat. It has 11 billion tons of salt separated perfectly from water. How? The sun. Evaporation is a distillation engine. We can use evaporation for purification, not just see it as a loss.
But that process takes geological timescales. We don't have 10,000 years. We have cities producing billions of gallons of sewage today. We need wastewater treatment plants. We can't wait for the sun to distill our water. We need sedimentation tanks. We need chemical flocculation, mechanical skimmers. It is high-tech, it is energy-intensive, but it keeps us alive.
Okay, but analyze your treatment plan for a second. How does the sedimentation tank actually work? You let the water sit still so gravity pulls the solids down. That's passive physics. And what do you do with a sludge cake that's left over? You use it as fertilizer because it's full of nitrogen? Even your high-tech concrete plant's just trying to replicate the natural nitrogen cycle. You're not escaping biology, you're just putting it in a concrete box and speeding it up.
We are accelerating it, yes. We are processing 144 million Olympic-sized swimming pools of wastewater a year. You can't do that with a salt flat. We have to inject energy to get the output we need. Which brings us to the ultimate lever of civilization, energy itself. If we want to talk about harnessing natural forces, let's talk about the force that holds the universe together, the atom.
Nuclear power. I knew we would end up here.
I mean, it is the only logical conclusion for a high-tech society. Fission currently generates about 10% of the world's electricity, and it does that without emitting the greenhouse gases that are destroying our climate. Think about the density here. A single pellet of uranium fuel, the size of a gummy bear, contains as much energy as a ton of coal.
And the waste from that gummy bear stays radioactive for 10,000 years.
But the waste is contained. Coal waste is just pumped into the atmosphere you breathe. Fission allows us to create a baseload, constant, unwavering power. And we're on the cusp of nuclear fusion, smashing hydrogen nuclei together to create helium. That is literally how the sun works. So my question is, why rely on a star 93 million miles away when we can build a small one in a reactor right here?
Because the star 93 million miles away is already built, it's already running, and it doesn't require complex containment fields to stop it melting our cities. Solar energy is the ultimate passive win. The physics are simple. The photoelectric effect. A photon hits a silicon cell, knocks an electron loose, and you have a current. No splitting atoms, no radioactive waste.
When the sun shines,
Which is enough! The International Space Station, the most high-tech object humans own, runs entirely on solar arrays. Those wings collecting sunlight are what keep the life support running. If it's reliable enough to keep astronauts alive in the vacuum of space, it's reliable enough for Earth. We have solar boats, like the MS Turnor Planet Solar, circumnavigating the globe without a single drop of fuel.
space is a different context. On Earth, we have night, we have winter, clouds. To run a 24-hour digital civilization, solar creates a deficit every single night. You can't run a hospital or a data center on weather-permitting power.
That is where energy storage comes in. And I'm not talking about chemical batteries that degrade like the one in your phone. I'm talking about big batteries that use gravity, like pumped hydro.
You mean pumping water uphill?
Yes. When the sun is shining and you have all this excess power, you use it to push water up a hill into a reservoir. That water sitting there is potential energy. When the sun goes down, you open the gates, water flows down through a turbine, and you have power. It's a battery made of water and gravity. We have flywheels that spin in a vacuum to store kinetic energy. We have suspended weights that lift and drop. These things don't really degrade. They harness Newton's laws, not volatile chemistry.
Those are ingenious, I admit, but they require massive geography. You need a mountain and a lake. Nuclear just requires a few acres. But you mentioned the space station, and I want to pivot there because space is the ultimate test case for my philosophy.
How so? Space is usually where high-tech reigns supreme.
Because it has to. On the International Space Station, there is no nature to help you. There's no atmosphere, no soil, no gravity. If you want to survive, you have to engineer everything. Look at how we grow food on the ISS. We're growing zinnias and red romaine lettuce. But you can't use soil. It would float around and destroy the instruments.
So you use hydroponics again?
We use pillows, protective pouches that are injected with water and nutrients, bathed in artificial LED light banks. In 2015, astronauts ate a space salad with red romaine lettuce they harvested right there in the module. In 2016, zinnias bloomed. This proves that we can strip away the whole messy context of Earth, the bugs, the soil, the weather, and sustain life through pure control. If we can do it in orbit, we can do it here. We don't need the complexity of soil, we just need the nutrients and the light.
See, that is where we fundamentally disagree. You see soil as messy complexity to be bypassed. I see it as a technology we haven't fully utilized yet. Soil isn't just dirt, it's a living chemical laboratory.
It's a medium. It has a pH level we can adjust.
It is so much more than pH, but fine, let's look at pH. If soil is too acidic, you don't just add a chemical, you kill the network. Farmers add lime to neutralize acid, not just for the roots, but because the earthworms and the mycorrhizal fungi, the internet of the soil, they die in acid.
But in my hydroponic tower, I don't need the worm. I am the worm. I provide the aeration, I provide the drainage, I provide the nitrates.
And by becoming the worm, you take on the responsibility of the worm. If the power cuts out, your aeration stops and your crop dies in hours. In a soil system, the biological momentum carries it through. You mentioned zinnias. On Earth, we have hydrangeas that change color from blue to pink based on the soil pH. That's a feedback loop. Nature is signaling us. High-tech approaches often treat the world as this blank slate to be written on, but it's not. It's a dense web of dependencies. And when you cut those dependencies to gain control, you actually introduce fragility.
I would argue that relying on a web of dependencies in a changing climate is the very definition of fragility. If the rain stops, the soil web collapses. We need decoupling. We need to secure the supply chain independent of the environment.
And I'd argue that decoupling leads to things like the Great Dust Bowl. When you treat soil like a factory floor instead of an ecosystem, it turns to dust.
We're reaching the end of our time, so that they summarize my position. The passive view is romantic. It's beautiful. Fog catchers and ice stupas are clever. But they are niche solutions. They can't support a global population of 10 billion. To feed the world, we need the industrial density of GM crops and vertical farms. To power the world, we need the energy density of nuclear fission. And to labor for the world, we need the precision of AI robotics. Science's greatest achievement is not mimicking nature, but overcoming its limitations to secure our future.
And I maintain that the idea of overcoming nature is exactly why we have microplastics in our blood and carbon in our atmosphere. Every time we brute force a solution, like covering a lake in plastic balls, we create a debt that we have to pay later. The most enduring solutions are the ones that align with the laws of physics instead of fighting them. Fermentation, gravity batteries, passive solar, these technologies do more with less. True scientific advancement is learning to be efficient by design, not just by output.
Perhaps the synthesis lies somewhere in the middle. We are seeing AI high-tech being used to monitor soil health, low-tech. We're using satellite data to find the perfect location for your fog catchers.
I can agree with that, using high-tech tools to better understand and optimize the low-tech natural systems. That is a future I can sign up for.
It's about using the right tool for the job. Sometimes that tool is a genetic editor, and sometimes it's just a mesh net.
Thank you for listening. We hope this debate has encouraged you to look at the objects around you, from the bread in your toaster to the battery in your pocket, and ask, is this fighting nature or working with it?
Thank you for joining us. This has been The Debate.